Hey everybody, in this video we're going to take a closer look at transmutation reactions for nuclear decay processes and go through some increasingly challenging examples of how to write these equations. That means ideally watching this video you've already learned what a transmutation reaction is. If you haven't, you can go check out one of my prior videos in this series to learn about them. And here's the first sample. So we've got 5 different equations that are partially done. Your goal is to fill out the missing particle in each box. Ideally, you're going to want to pause the video and try these yourself first before clicking play again to watch me go over the answers. Assuming you've done that, or if you just want to follow along, here we go. We're starting with, on the left side of the arrow, 98 total protons. And that means on the right-hand side, we also need to have 98 total protons. 42 of them are here, 0 of them are here. So that means a quick subtraction, 98 minus 42. My missing particle has 56 protons, making this an atom of barium, which you can look up on any periodic table. If we do the same thing with the masses, you can see I'm starting with 252 mass units, which means total on the right-hand side, I've also got to have 252. This symbol is a little bit confusing maybe, that large 4 out in front of the symbol for a neutron. If you weren't sure what that means, essentially that's saying that you've got the symbol for a neutron written 4 times. You know, the alternative to writing it this way, like you're seeing here, would be to actually do that, actually write out that neutron symbol 4 times. This matters so I know how to add up all of these mass units. So we've got 106 of them here, a total of 4 mass units across all 4 of those neutrons. And again, a quick subtraction to find out the amount of mass units that's left from my missing particle. The 252 I started with minus the 106, and then again minus the 4 gives me a total of 142 leftover mass units to fill out for my barium. That means officially I have produced an atom of barium 142. In the second example, the missing particle is on the left side of the arrow, so I have to actually start on the right-hand side to see that I've got a total of 6 protons. I've got to have that same total of 6 protons then on the right. Since 4 of them are here, my missing particle is going to have 2 of those, and I now know that it's a helium atom. As far as the masses go, I've got a total of 12 plus 1, 13 on the right-hand side, so I need the same 13 on the left. 9 plus 4 would give me the 13. So my missing particle is a helium-4 atom. In the third example, we have 2 elements that are coming together on the left-hand side, and on the products, I've got a fluorine-17 and my missing particle. On the left, a total of 3 plus 6 protons is 9, and I've already got 9 protons in my fluorine. That leaves 0 protons for whatever my missing element is. Back to the left, I've got a total mass of 6 plus 12, 18. 17 of those units are here, leaving just 1 for this missing particle, and that's describing, of course, a neutron with the numbers 0 and 1. In the fourth example, cobalt-60 is colliding with something coming together to produce iron 2660. Since I've got a total of 26 on the right, I need that same total of 26 on the left. The only thing I can add to 27 to get 26 is that -1. 27 and -1 is the 26 I need. The masses of both of these are already 60, so my missing particle will have a mass of 0, and that's of course describing an electron or a beta particle. In the last example has 2 helium atoms colliding together to make beryllium-7 and some missing particle. At the beginning on the left, there's a total of 2 plus 2, 4 protons. I've already got 4 protons in beryllium, so the missing particle has 0. On the left, there's a total mass of 8. My beryllium has 7 of those 8, so the missing particle must have 1 mass unit, so we again have a neutron. And that's the complete set. We're going to move on and look at some other nuclear changes to learn about what they are, but also practice some more complicated transmutation reactions, starting with nuclear fusion. You've probably heard this word before. This is when 2 or more nuclei combine, or essentially come together to make 1 or more larger new nuclei. This is what happens in the sun, where hydrogen atoms and helium atoms collide together, fusing together, making larger atoms and lots of heat and energy in the process. That's what's being described here in this sentence. Hydrogen 2 and hydrogen 3 fuse together, producing a new neutron and what new atom? I always like to begin by putting the arrow just to establish whatever's in existence before the change and whatever's in existence after the change. And you can think about this word producing as kind of like representing that arrow and telling you what should be written before it and what should be written after it. Let's actually start with that. It says producing a neutron. So I'm going to start with that, producing a neutron, and there's my neutron symbol. It says a neutron and what new atom? So there's going to be like some new mystery atom that's there after the fact. Before the arrow, it says we've got hydrogen 2 and hydrogen 3 fusing together. So there's my H2, there's my H3. The periodic table tells me each of those hydrogens has one proton. And now I can sort of do like we did at the beginning of the video, and use these numbers to predict essentially this new atom, this missing particle. The two hydrogens have a total of 2 protons. The neutron's got 0. So this new particle must also have 2 protons and must be helium. The total mass on the left is 2 plus 3, 5. The neutron has 1 of those units, leaving behind 4 for my helium atom. And there's the complete transmutation reaction for that sentence. Another common nuclear change is the opposite of fusion, and it's called fission. This is what humans can accomplish in the extremely destructive weapons known as atomic bombs. Here's some videos of atomic bombs being tested in places like oceans and deserts. And here we've got a definition of fission, which says it's one large nucleus that's being split into smaller fragments. Here's a description of one of these examples. Let's see if we can turn this into a transmutation equation. It says a neutron collides with uranium-235, producing, so that defines where my arrow is going to be, producing 3 neutrons. Now, you could choose to write 3 neutrons like this with the neutron symbol 3 times over. I like to be a little bit faster about it and just write that symbol 1 time, but with a big 3 out in front. But you could do it either way. So we're producing 3 neutrons, krypton 92, so Kr 92. Of course, the periodic table tells me krypton has 36 protons. And what new atom? So there's one more symbol that I need to wait on. First, let's fill in what's happening on the left-hand side of this. It says a neutron collides with uranium-235. So here's uranium-235. Uranium's got 92 protons. This whole process is triggered by a neutron sort of smashing into that uranium. And now I've got my total quantities to figure out what these missing particles are going to be. On the left, there's 92 total protons. 92 minus the 36 in krypton tells me that my new particle must have 56 protons and is there for barium. The mass of this barium comes from the 235 plus 1. That's a total of, let's switch to green here, a total of 236 mass units on the left. I need those same 236 mass units on the right. If I start subtracting them out, 236 minus 3 mass units here from my 3 neutrons, also minus the 92 mass units in krypton, leaving behind 141 mass units for my barium atom that is produced in this process. Next up, we've got something called electron capture. This is sort of like the opposite of a beta decay, where a nucleus actually absorbs an electron, and this happens often producing a more stable nucleus. Oddly enough, one place that it happens is in bananas. The description here says potassium-40 in bananas can undergo electron capture, producing what new atom? Let's begin by writing the symbol for potassium-40. If it's capturing or absorbing an electron, we're going to write that electron symbol being combined with or added to the potassium prior to the arrow. Essentially, these 2 particles are fusing to become 1 particle, and it says producing what new atom? Of course, 19 plus -1 is 18, so my new atom must have 18 protons, which makes it argon with a mass of 40. Interestingly enough, the fact that this happens is part of why that our atmosphere contains a very small percentage of argon atoms. A lot of those were produced by potassium atoms in vegetation, like bananas, undergoing electron capture. The very last one is another cool thing that human beings can do called particle collisions. There's these gigantic instruments called particle colliders where atoms and lots of other small particles, but typically atoms, are spun around big giant loops, big giant tracks, typically underground, really, really fast. Then they smash them into each other, and as they do that, they can break down and decay and sometimes fuse together, producing new, larger nuclei. Here's some images of one of these tracks inside that blue tube. This is where your atoms would be accelerated to close to the speed of light before they eventually collide and smash into one another. Let's read the description and see if we can write a transmutation reaction for one of these. Plutonium-244 and calcium-40 ions are collided, producing, here's my arrow, what large new atom? So if you're told that two atoms are being collided, you're going to show their two symbols being added together on the left-hand side of the arrow, starting with calcium-40, that looks like this, and plutonium-244, that looks like this. Based on the sentence I'm given, it says it's producing just one single large new atom, so we've just got to add these numbers together. 94 plus 20 is 114, 24 plus 40 is 284, and element 114 is called flerovium, symbolized Fl. That also wraps it up for this lesson on transmutation reactions. Thanks a lot for watching.